Okay, in this session, we will just check your these two exercises from your homework. We will not solve the entire exercise, but we will give you, I think, that some good ideas for the solution. The first one is very easy, but we will read it. It says that we have to consider a portfolio of n independent one-year term life insurance policies, and each one with a different insured amount, CJ, for J between 1 and N, okay? And then we have to consider an individual risk model where each individual policy claim is modeled by a random variable xj that is equal to the value of the amount CJ times Bj, where each Bj is a Bernoulli random variable with a parameter Qj, okay? And it asks us to obtain explicit formulas for the mean and the variance of the total claims, okay? This is a very, very easy exercise, and it is, I think, that quite simple to understand, but it is important to understand this part, the Bernoulli random variables parameter, because what it says here is that the xj random variables can take only two values, okay? Because if, for example, the Bernoulli random variable can take the values 1 and 0, and if the Bj random variable takes the value of 1, then the xj random variable will take the value of Cj, that is the insured amount for that policy, okay? Instead, if the Bernoulli random variable take the value of 0, the random variable xj will take the value of 0 too. So this is one way to model that the random variable just can't take the value of 0, that is when the insurance company do not pay anything, and the value of Cj when the insurance company pay the insurance amount CJ. There are only two possible cases, and that is because this is a life insurance policy. In the most of the life insurance policies, we just have that two specific cases: to pay all the insured amount or to pay nothing, to pay 0. Okay. So now, to obtain the explicit formulas for the expected value and the variance, we will just first have to remember that the total amount of the payments will be a random variable S. That will be defined as the sum, as the aggregation of the random variables xj, okay? And in this particular case, this will be the sum of these CJs times BJs random variables, okay? And to calculate the expectation value of S using this is very, very easy, because the sum of the expectation values is the expectation value of the sum, and then we can just calculate the expectation value of one of the xj random variables, and this would be the expectation value of Cj times Bj, and since Cj is a constant, we can take it out of from the expectation value, and then we will just have Cj times the expectation value of the Bj random variable, that is a Bernoulli. So a Bernoulli random variable has the property that its expectation value is the parameter of that distribution, that in this case is Qj. So then the expectation value of xj will be just Cj times Qj. I think that is very easy to see. And with this, we will just have to note that then the expectation value of S is the expectation value of this sum of random variables. Then we can just take the sum out of the expectation value, and we can substitute in the sum this value that we have just calculated, and then the expectation value of S will be the sum from 1 to n of the values Cj times Qj. And now, if we want to calculate the variance, we can do something very similar, because in this particular case, we have that we are supposing that the random variables xy to xn are independent, and then the variance of S would be the variance of the sum of random variables, but since these are independent, we can compute this as the sum of the variances, okay? And I mean, you can compute the variance of the xj random variable is very similar to this, using that the bj is a Bernoulli, and you can get the result. No, I won't do it because it's your homework, but it's very, very similar to what we have done for the expectation value, okay? And also another way that you can do all these calculations will be first computing the probability max function of the random variable xj, okay? That is the probability for that random variable to take a specific value, little x, and using your heads, okay, you can just see that if that little x value is 0, then the probability for this random variable to be 0 would be 1 minus qj, because remember, in this exercise, qj is the probability for the policyholder to make what's the word, to die. Okay, well, while since this is a life insurance policy, here will be qj will be the probability that the policyholder dies, okay? So if the policyholder do not die, that the probability will be 1 minus qj, the insurance company will pay nothing, okay? That would be when xj takes the value of 0. And the other case is when the policyholder dies, and then the insurance company will pay the insured amount CJ, and that is with probability QJ, okay? This is the probability for the policyholder to die, okay? And then if you have this expression for the probability mass function, you can compute the expectation value using the expectation value formula for discrete random variables that we learned in probability, and that would be, in this case, the expectation value of the random variable, the value of 0 times the probability for the random variable to take that value. Then this will die because it's 0. And then we have to add the other value that this random variable can take, that would be Cj, times the probability that the random variable take the value Cj, that is Qj. So we will get the same answer, Cj times Qj, and then we can just do this, okay? This calculation. The answer will be the same. This is the expected value of the random variable S, and I repeat, you can do a similar calculation for the variance. Yes? Okay, so this was an easy one. We will now go to the interesting one, okay? This is a long one. It says, consider a portfolio of 1-year term life insurance independent policies from the file, okay, this file that is in the page in the classroom, okay, that specifies age and insured amount for each policy, okay, with the additional benefit of twice the insured amount in case of accidental death. This is very important in this exercise. Then we have to assume that 1 out of 10 deaths is accidental, and no matter the age. And we have to use the mortality table that is in this other file, okay, that is also in the classroom. And we have to do all the following steps, okay? So in the classroom, we have 2 files. The first file has the age of the policyholder and the insured amount for that policy, okay? And that is for 10,000 policies, for 10,000 different policies with different ages and different insured amounts, okay? That is what is in this file. And in the other file, it's a mortality table, like in actuarial mathematics, that it says to you the probability from a certain age to die in 1 year, okay? So the thing is that there are in this file there are 10,000 policies, so there are a lot of policies, but okay. So the first step that it says that is that we have to calculate the theoretical mean and variance for total claims, okay? Then it says that we have to make 60,000 claim simulations for the portfolio. And then with that simulations, we have to estimate the mean and the variance of total claims, and then compare that estimation to the theoretical values that we obtained in the previous item, okay, in the item A. And then the item C says, also from item B, estimate the value at risk of level 99.5, for total claims, okay? And then using the first item results, okay, the mean and the variance, the theoretical mean and theoretical variance, we have to calculate with a normal approximation. We will see what that means. The bar of level 99.5, okay, and then compare it to the estimation of the bar with the simulations, okay? And then we will have to graph an histogram from the simulations and compare it to the graph of the normal approximation of the previous item. So it's a very long exercise, and it's an exercise where you will have to use a computer, of course, to make those simulations. But here we will not solve it, but we will analyze how you can solve it in your own computer. And I hope that this will be very helpful for you. So now, for this, we will have to first model this exercise to get the formulas. And in this case, we have an individual risk model with n equal to 10,000, because in the file you will find the information for 10,000 different policies. So n will be 10,000. Well, a big number. And then the random variable that we are interested in is the sum of the amount paid for each of the 10,000 policies. Okay, so it would be a sum it would be an aggregation of 10,000 different random variables. So this is kind of crazy to solve without using any computational tools. Okay, this would be crazy not to sum 10,000 random variables, but we will use the computer, or well, you will use the computer, because here we will just see the theory, like the theory of the problem, but then the implementation is on you. Okay, so now if we have a value j between 1 and n, then in this case is between 1 and 10,000. In this case, the random variable xj, that remember is the amount paid by the insurance company for the policy j. In this case, that random variable could take the next three values. Can take the value of 0, can take the value of cj, that is the insured amount for that policy, and can take the value of 2 times cj, because it says that in case of an accidental death, they will have to pay twice. Okay, so it would be 2 times cj in this case. You can find these values of cj's in the file. Okay, in the first file. But we will just speak about cj to do it in general. So now there are two ways to model this. I believe maybe there are more, but I think about two ways. The first one is like defining an auxiliary event to calculate how would be the probability mass function of this random variable. Because if you want to simulate this random variable, you will have to calculate, for example, the probability mass function of the probability distribution function of this random variable, and then you will be able to simulate that distribution. Okay, so we will first have to calculate, in this case, because it's a discrete random variable, because it only has the 3 possible values, it is easy to compute the probability mass function. So that is what we will calculate now. And for that, we will just define this event. We will call it AJ, and that is the event of the jth policyholder suffers an accidental death. Okay, that will be an event that is possible in our random experiment. And the problem says that 1 out of 10 deaths is accidental, no matter the age. Okay, so we can write that using conditional probability in this case, because if we know that the policyholder has died, that would be, for example, this event when the insurance company pays something positive, would be xj greater than 0, that event. This event represents we pay, so that is because the policyholder of this jade policy dies. So in that case, if we want also to be an accidental death, that would be this event. That probability, that conditional probability, that given that we have a death, we want it to be accidental, would be 1 over 10, because it says that 1 between 10 deaths, it's an accidental death, and that is just 0.1. Sorry. And this also can significate that in the same case, given that the policyholder of the jade policy died, the probability that wasn't an accidental death, that would be the complement of this event, would be 1 minus 1 over 10, or 9 over 10, that is 0.9. So now, if we have this auxiliary event to write this way, that fact that 1 between 10 deaths is an accidental, we can compute then the probability mass function of this random variable. For example, the first value that this random variable can take is 0. That is an easy one. The probability for that random variable to be 0 is similar to the other exercise. It would be just 1 minus qj, because it is a probability for the policyholder to live, to not die in that year. Okay, so, and also since these are the only 3 cases, and cj would be a positive value always because it's the insured amount, this also means that the probability of this event, the 2xj be greater than 0, would be qj, that is the complement of this event. So then, if we want to compute the probability for the random variable to be equal to cj, that would be in terms of events. First, that the policyholder died, that is when xj is positive, but also if it is equal to cj, it's because it's not an accidental death, so it would be the complement of the event that we defined, that it was when the policyholder suffers an accidental death. Okay, so we will need this intersection of events, so then the both would be true. This is the probability. This event is when this random variable is equal to cj. It's the same event, so the probability will be also the same. And then we can compute this probability of an intersection using conditional probability properties. For example, we can see this as the conditional probability of the event AJ complement given that the random variable is positive times the probability that the random variable is positive. For example, if you substitute the definition of this conditional probability, you will see that you will get this intersection, the probability of this intersection. That is because that is the reason that we can compute this in terms of this. And we have already this probability. This probability, the right side is Qj, and the left side is the probability that we were talking about, that would be, in this case, 0.9. So using this little trick, we can compute the probability for xj to be cj equal to 0.9 times qj. In a very similar way, we can compute the probability of x to be equal to 2 times cj. It will also be the intersection of two events, but in this case, the first event when we pay something because the policyholder dies, and in this case, we want that debt to be accidental, so then the value that we pay will be 2 times cj, and with a similar step, we can get that this probability would be 0.1 times qj. Okay, if this was clear, this would have also to be clear. So with these three values, 1 minus qj, 0.9 times qj, and 0.1 times qj, we can write the probability mass function of x in terms of these three values and the corresponding indicator functions. It's what we have here in red. And then using this probability mass function, you can simulate the distribution of this random variable, and also, of course, in the table you will have the specific values of qj in the mortality table, and in the other file you will have the specific values of cj, and then you can get the specific value of 2 times cj. So for a specific j in the exercise, you will have a different probability mass function, but they will all have this structure. Okay, so you will have to make a simulation for each of the different probability mass function for each of the different specific values that there are in the first and second file. Okay. Another equivalent way to model this would be defining the next random variables. Okay, you can define a random variable yj in this way. It would be equal to 2 if the jade policyholder suffers an accidental death. It would be equal to 1 if the jade policyholder suffers a non-accidental death, and it would be 0 in other case. So if you define these random variables, then you can write xj equal to cj times yj. And this works because, for example, if the policyholder suffers an accidental death, you will have to pay 2 times cj, and this random variable in that case will get the value of 2, and then the payment xj will be 2 times cj as we want. Also, in the case of a non-accidental death, this random variable will be 1, and then xj would be just 1 times cj, so that is what we want. Okay, in other case it would be 0. So now, using this random variable, this auxiliary random variable, we can get the expectation value of xj, or also using the probability mass function that we compute in the other way. And we can get the value of this expectation value. And then the value of the expectation value of S would be the sum of these other values, okay? And similar with the variance, because we are assuming that the xj random variables are independent. So now, for example, we will compute this, then you will have to compute this by your own. Using the probability mass function, for example, would be the expected value of xj would be 0 times the probability for that variable to take the value of 0. This will die. And then cj times the probability that that random variable to take the value of cj, that was this one. And 2 times cj times the probability of the random variable taking the value of 2cj. And doing a little bit of algebra, we can get that this total expected value would be, for example, if we factorize cj times qj, we will have this 0.9 adding 2 times this 0.1, that is 0.2, and then 0.9 plus 0.2 is 1.1. So the value of this expected value is 1.1 times cj times qj, okay? And then the expected value of S in this particular exercise will be 1.1 times the sum of these values, cj times qj, and the sum from 1 to 10,000, that is the number of policies that we have in this particular case, okay? And you can get a similar expression for the variance. This is easy. And then this would be like the theoretical answer for the item A, but since the professor has uploaded the file with the specific values of cj and qj, you will have to evaluate this theoretical formula with the specific values of the file. So then you will get a numerical answer, and a specific numerical answer. Of course, there is a sum with 10,000 terms, so you will have to use a computer to calculate this, of course. But you can get a specific numerical answer, okay? Also with the variance. And now, that will be the item A. And for the items B and C, I will try to explain what is the logic of the simulations that you will have to do in case you do not understand it very clear. You will have to simulate these 10,000 random variables. Okay, the 10,000. There are a lot of simulations that you will have to do. 10,000 simulations, one for each random variable, because each random variable has their specific value of cj and their specific value of qj that there are in the files. Okay, and how can you do this? You can use the probability mass function that we have compute, or here is a little mistake. You can use this other expression, because you can find a way to simulate this random variable yj, that is a very simple one, and then you will have to use this transformation, just multiplicate it by cj. Any of the both ways you can simulate one of every of these. You can simulate all these 10,000 random variables. There are very easy ones because there are discretes, and then once you are able to simulate these 10,000 random variables one time each, you have to use the simulated values that we called in this case, for example, x1, 1 to x1, 10,000. The first one is because this is the first simulation of this random variables that we will make. And the second number is associated with the number of the policy. So we will get 10,000 values that we can call it like this. And then with these 10,000 values, you can get a simulated observation of the random variable x. Remember, the random variable x is the sum of these 10,000 random variables. So then, to get an simulate observation of this, you can call it S1 because it's the first one. You can sum these simulated values of these 10,000 random variables. Okay, so to get just one observation of S, you have to do these 10,000 simulations, and then you have to calculate the sum of that simulations. Okay, so this is the first observation. No, that is because the first number of this X simulation is 1. It's fixed as 1, and then you will have to repeat this process 60,000 times because you want to get 60,000 simulated values of S. So at the end, the total number of simulations that you will have to do would be 60,000 times 10,000, because for every simulation of S, you will have to do 10,000 simulations, one for each of these random variables, and the total number of simulations will be 600 million of simulations. So there are a lot of simulations. So now that you have these 60,000 simulations of S, you will be able to estimate the expected value of S and the variance of S using this 60,000 simulation of S. How can you do this? For example, you can take as an estimation for the expected value of S the sample mean of these simulated observations, that in this case would be 1 over n, 1 over 10,000, the sum times the sum of the simulation of S, of the simulated observations of S. Okay, so no, sorry. Here is not 10,000. Here is 60,000 because we will get 60,000 observation of S. And similar to this, you can get the estimator for the variance of S as 1 over n minus 1, that in this case would be 59,999. And then the sum over the 60,000 values, that will give you this expression. Take one of the simulations, each one of the simulations, then minus this estimation of the expected value, and then that difference you will have to square it. Okay, so and then add all these possible values, changing the value of the simulation of S. This will be the same always, but this will change. Okay, so this is a quite good estimator for the variance of the random variable, in this case for the variance of S. So once you have these 60,000 values, you can calculate this one and this one, and you will get a specific number, and that will be the estimations of the expected value of S and the variance of S, and you will be able to compare these estimated values with for example, with the theoretical expectation value that you calculate in the previous item. Okay, in the item A, and also with the variance. Okay, so you will see if these are good approximations of that values. And also, if you want to estimate the bar, you may use, for example, as an estimator of the bar, point at a level 0.995, you can use the order statistic for the S observations. 9,950. So remember, the order statistics is when you order all your observations, in this case your S simulations. Sorry. This is wrong. You will have to get something like this. So okay, sorry for that. Now I wrote it correctly. The estimator that you may use for the bar in this case would be the order statistic, but it won't be the number that I had right before. It would be the number 59,000 700. Okay, and I also correct that I wrote big S, and it's more accurate to write little s, because you will have to use the order statistic, but of the simulations that are like the simulated observations. So if you write big S, you would be referring to a random variable, and we do not want that. We want to refer to an simulated observation, so I wrote here little s, just as here and as here. Okay, but why do we use an order statistic of this level to estimate the bar? That is because remember that the bar is a number where we have in the left of that number the 0.995 probability of the distribution. Okay, well, you can get it in an alpha level, and this will be also an alpha level, but in this case we want this specific number, and it's the value that accumulates this specific probability. Okay, so if we want to estimate that with our simulated observations, we will have to choose a value between those simulated observations, so that the 99.5% of the values is in the left of that simulated observations, to have something like the 99.5 of probability to be left in the left side of that observation. Okay, something like that, just like the theoretical value. And in this case, the 99.5%, okay, that will be this factor of 60,000 is equals to 59,700. So that is the reason we choose this number, this specific number. And this would be a very good estimator for this theoretical value. Okay, so the idea would be to calculate this simulated value of the bar, and then you will have to compare it to a theoretical value of the bar. But in this case, we do not know which is the exact distribution of this random variable. That is, for example, the reason for simulate that random variable, to get an approximation of the distribution. But what we can do is to get a normal approximation of the random variable. And then with that normal approximation, we can get a normal approximation of this value of the bar at this level. That would be for the item D of the homework, of the exercise of the homework. And we can remember that if we use the central limit theorem, we can approximate this random variable S minus the expectation of S divided by the square root of the variance of S, the standard deviation of S, I believe is the word. Okay, the square root of the variance of S, okay? The central limit theorem says that this random variable, when n, in this case n, n would be the number of random variables that you have in a sum. When n is a sum of independent random variables and n tends to infinity, these random variables tends to a normal approximations with parameters 0 and 1. In this case, we have n equal to 10,000. That is a big number, okay, but that is not infinity. So in this case, we cannot say that this is an exactly normal random variable, but it would be very similar. The distribution of this random variable would be very similar to an standard normal, a normal distribution with mean 0 and variance 1. And if this is true, then the random variable s would be very similar to a normal approximation with mean equal to the expected value of s and variance equal to the variance of s. You can just use like the transformation properties for the normal when you multiplicate by a constant and some another constant, and you can get that if this is true, this would be also true. Okay, that is not really difficult to get a justification. And this is the way that we can use the central limit theorem with an approximation, okay? With these specific kinds of approximations, when you have a random variable that is a sum of independent random variables, you can use this specific approximation with a normal distribution. And in this case, we have that s would, well, if we have a random variable s, okay, this is not like a continuation. This would be just like a recall, for example. Okay, if we have a normal random variable s with mean mu and variance sigma squared, and we define x as the value at risk at the level alpha of s, this would mean that the probability of s being less or equal than little x would have to be equal to alpha by definition of value at risk. But if we get a normal standardization here in this event, we will get that s minus mu and then divided by sigma would be less or equal than little x minus mu and then divided by sigma. And in this case, if s was a normal distribution, this would be also a normal distributed random variable, but with parameters 0 and 1. And in this size, this would be the value c sub alpha, that would be the inverse of the distribution function of this distribution, that is also denoted by this Greek letter phi. Okay, and these are the values that we can get in the tables, or for example in the computer programs for the standard normal distribution. Okay, it's very common to have these values in a table, for example. So then, if this was the case, we would have that this number c sub alpha would have to be equal to this one. So we will get this equation, and if we want to get what would be the bar, but not of this random variable, for the s random variable, we can just leave the little x alone, and we will get that x, the bar of s, would have to be equal to mu plus sigma times this value. Okay, so if you want to calculate the value at risk of any normal random variable, you can just use these values that you can find in the tables of the standard normal distribution to get this. Okay, so the bar would be this expression. So this was like a recall. So now in our case, we do not have that s is an exact normal distribution, but it can be approximated with a normal distribution. So then the bar of s would also can't be approximated with the bar of this normal distribution. In our case, we will have to use this formula, but with mu equal to the expected value of S, the theoretical expected value of S that we can calculate, of course, with the formulas that we calculate before. And we will have to use sigma with this equation. Okay, sigma squared would be the variance of S. So then sigma will just be the square root of the variance of S. Okay, and also in this specific case, for C sub alpha, you will need specifically C sub 0.995, and a very good approximation for this value you will find that is 2.575083. Okay, you maybe can get a better approximation, but this is a very good one. Okay, you can use this one. And now, to end this session, we can quickly see this little simulation tip, because if we want to simulate S, we have to simulate the random variables xj, and to simulate that we can use this. Okay, we can remember that we can write xj in terms of cj and another random variable yj. So to simulate the distribution from the random variable yj, you can simulate a random variable u with a distribution, with an uniform distribution between 0 and 1. This is very easy in a lot of computer programs and computer programming languages. This is a very easy command. And you have to consider this transformation for this random variable that you are simulating. You can use a random variable y. Okay, that would be the transformation of u, and this would be 0 if this random variable u is between the values 0 and y minus qj. So with this you can be sure that the value of 0 would have the probability 1 minus qj. That is what we want with the distribution of this random variable. And this random variable will have to get the value of 1 if the random variable u is between the value 1 minus qj and the value 1 minus qj plus 0.9 times the value of qj. Why between these values? Because then the probability to get a 1 would be the probability for you to being in this interval. So it would be just the length of the interval, and the length of this interval is just this value as we want. And then for the value of 2, we will have to get it if the random variable u is between this other value and 1. So then the probability for 2 would be 1 minus this value, and 1 minus this value is just 0.1 times qj as we want. So this is a good trick to simulate the distribution of these random variables yj with this with this kind of transformations. Okay, obviously the values of qj would be defined in the file, so you will have a different value for each j, and you will have to make a computer program to simulate the distribution of these random variables in terms of a random and in a random variable with distribution uniform between 0 and 1. Okay, maybe you can use a more clever way to simulate this distribution, but this is I think that is a very easy one.